Welcome to the next lecture, where we will see some properties of fluid. Properties of fluid is a very important lecture. Once you understand the property of the fluid, then you can see how this can be mapped to real-time application. For example, I try to have a polymer which is coated on top of a tire. Now, as soon as there is a leak in the tire, the polymer is expected to freeze and seal the hole. Now, I should choose a polymer which has a flowability property. I should choose a polymer which is light in weight, which does not add weight to the tire. The coating thickness should be uniform. The fluid which forms the film has to be also tailor-made. This is one application. Let's take another example wherein which I would like to take fluid in a container. Now, I have to plan the size of the container with respect to the fluid. So, now the weight of the fluid plays a very important role. So, now you see the properties of fluid are very important for us to understand. In thermodynamics part, we saw boiling phenomena, we saw vaporization phenomena. So, all these things are subjected to a temperature property. So, if I want an application wherein which the liquid should boil faster, the liquid should vaporize faster, then what do? Is I try to choose those properties which are required to bring in this application. So, friends, properties of a fluid is very important. So, here in which we will try to see majority of them. There are 100 different properties of fluid can be characterized, or the properties play an important role. We will choose some which are very important for general applications. First, we will try to see specific weight and density. Then there is a terminology called as specific gravity. We will see that also. Then viscosity. Viscosity is very important because when you try to pour ketchup, you try to squeeze and then the ketchup flows. If the flowability property is very high, so then what happens? With a small press, a large amount of fluid will be discharged. So, viscosity plays a very important role. Then it is non-slip condition in fluid, surface tension, capillary action, compressibility in the fluid, vapor pressure and cavitation, bulk modulus and its indicator role, specific heat and thermal conductivity in a fluid, Cp, Cv in a fluid, then significance of thermal expansion, and then ideal fluid and real fluid. Finally, we will see some applications with the effect to temperature. A fluid is a substance that continually flows or deforms when we subject it to shear stress or external force. This is a rebrush of the previous lecture. The solid can resist a shear stress by a static deflection. A fluid cannot resist shear stress by a static deflection. Any applied shear stress, no matter how small, will cause the fluid to move and deform continually as long as the stress is applied. So, there is a fluid, you are trying to push the fluid, it will try to go. The fluid at rest must be in the state of zero shear stress, which is known as hydrostatic stress condition. Density is defined as the mass per unit volume of a fluid. For gases, the density is highly variable and increases nearly proportion to the pressure levels. So, for gas, pressure plays an important role. In liquid, the density is nearly constant. For example, the density of water is 1000 kg per meter cube, which increases only by 1% if the pressure is increased by 220 factors, which is the pressure is increased by a factor of 220 times. So, now it is very clear the density of gas can be increased by increasing the pressure. So, that is how you have LPG cylinders, CNG cylinders, liquid nitrogen cylinders. Generally, liquid are about 3 orders of magnitude more dense than the gas at the atmospheric pressure. Specific weight and its unit. The specific weight of a fluid is denoted by a term called gamma, is its weight per unit volume. The density and specific weight are related by gamma equal to rho times g. So, in SI units, we will be representing it as Newton per meter cube. When we talk about specific gravity, specific weight is different, specific gravity is different. Specific gravity is known as a relative density, is used to describe the density of a substance compared to the density of water. I know water's weight. Now, I compare and try to say the existing fluid's weight or density. So, this is what is specific gravity. And why is it important? Because many a times the general fluid used is water. So, now if I know the specific gravity with respect to water, what is the difference I can understand and accordingly develop a system for it. To calculate the specific gravity, we divide the sample density by the density of water. So, the formula is density of the object or the given fluid divided by density of water, rho object by rho water. Then friends, there is something called as mass density and weight density. The density is denoted by a term rho, which is defined as mass per unit volume of the fluid. When we talk about weight, it is denoted by gamma and it is defined as the weight per unit volume of the fluid. So, the density is an important parameter when we are trying to place cork on top of a fluid, wood on top of a fluid, aluminium on top of a fluid and lead on top of a fluid. So, the density is very important. This is generally we are keeping the varying solids, but the liquid density is also very important. The density and specific weight are related by the term gamma equal to rho g. The density is highly variable in gas, increases nearly proportion to the pressure levels, while in liquid the density is nearly constant, which increases only very small percentage by pressure. Viscosity. Viscosity is defined as a quantitative measure of the fluid's resistance to flow. When a medicine is poured into a plastic container, when a medicine is poured on a spoon, when honey is taken from the container, all these things if you see, there is a resistance for the fluid to flow. So, measure of the fluid resistance to flow and relates to the local stresses in a moving fluid to a strain rate of the fluid element. So, this is very important. Viscosity plays a very important role. When we try to paint a surface, the paint should have a viscosity such that it gives a small thin film thickness, plus it should also be able to flow. If it is fully flowing, then it is of no use. So, you should have a combination of these two, quantitative measure of the fluid resistance to flow and relates to the local stresses in a moving fluid to the strain rate of the fluid element. More specifically, viscosity determines the fluid strain rate generated given applied shear stress. The common fluid like water, oil has a different viscosity, and air exhibit a linear relationship between applied shear stress. This is stress by strain. Right? So, viscosity can be like this. So, the common fluids like water, oil, air exhibits a linear relationship between applied shear stress and resulting in strain rates d theta by dt or du by dy. So, the constant of proportionality in its linear relationship is the viscosity coefficient mu. So, the tau is the shear stress, which is equal to mu times d theta by dt or mu times du by dy. Fluid that follow this linear relationship are called as Newtonian fluid, and those of it which does not follow is called as non-Newtonian fluid. The magnitude of the viscosity varies vastly among common fluids, spanning 6 orders of magnitude from hydrogen to glycerin. So, you can see glycerin is thick, there are 6 orders of magnitude higher. So, viscosity plays a very important role. What will be the time taken to fill a container? That viscosity plays a very important role. Then what will be the residual which is left in a container? Again, viscosity plays a very important role. So, if you take ghee, it is a viscous fluid. So, when it is given coating on top of a pan, so that tries to talk about the viscosity of the fluid, trying to help in forming a thin film with minimum efforts. The other way around is, if you see, people are very smart. What they do is they heat the pan and then they pour ghee on it, and then they rotate the pan such that the uniform coating is given. So, there what happens is ghee, which is little viscous, by the effect of temperature becomes much more thinner film so that it can easily spread. The kinematic and dynamic viscosity. Viscosity has two parts: kinetic viscosity and dynamic viscosity. Dynamic viscosity, denoted by nu, is the viscosity coefficient discussed above. It relates shear stress directly to the velocity gradient. Whereas kinetic viscosity nu, it is the ratio between dynamic viscosity to density. Friends, look at this difference. Dynamic viscosity is different, kinematic viscosity is different. Kinematic viscosity is a relationship nu which is equal to mu divided by rho. So, it is called as kinematic because the mass units cancel out in the ratio, leaving only the dimension L square by T or L square T inverse. So, that is why it is called as kinematic viscosity. The dynamic viscosity is tau, what we saw, tau by d theta by dt, or you can have it as du by dy, linear. This is dynamic viscosity, and you have kinematic viscosity. The SI units of dynamic viscosity mu is kg per meter second. This is equivalent to Newton second meter square. The kinematic viscosity nu will be expressed in meter square per second, m square by s. So, the units are different. So, the understanding is different. No slip condition in fluid motion. No slip condition is a characteristic of all viscous fluid flow. It states that the fluid velocity at a solid wall is 0 relative to the wall. So, you have a wall, you have a liquid which is sitting there. So, we stated it states that the fluid velocity at the wall, solid wall, is 0. There is no velocity relative to the wall. Inviscid flow, in contrast, do not satisfy this condition. So, they slip at the wall but not flow through it. They slip at the wall and not flow through it. These are inviscid flow. This condition is demonstrated experimentally by techniques using hydrogen bubble to visualize velocity profile near the wall, which shows zero velocity right at the surface, and subsequently it keeps moving. So, this condition is demonstrated experimentally by techniques like using hydrogen bubble to visualize velocity profile near the wall. Viscosity variation in liquid and gas. For liquids, the dynamic viscosity mu generally decreases as the temperature increases. That's what I said. So, when you try to heat the pan, put a spoon of ghee, heat it. What happens is it gets into liquid so that it can flow. You take a solid coconut oil during winter, put it in your hand, press it and create a friction heat, it becomes liquid. So, this is a temperature, right? Viscosity decreases with temperature. For gases, dynamic viscosity increases with temperature. As the temperature goes high, the dynamic viscosity in gas increases. The change in viscosity, please understand friends, you should make use of these properties. Don't try to just read it and then memorize it. You should make use of these properties in your real-time application. If I come to know that dynamic viscosity generally increases as temperature increases for a gas, now you are trying to use a gaseous medium and want the gaseous medium to do some job. So, now you can try to choose gases wherein which the viscosity, the resistance to flow increases with temperature. So, it can be used for shutting or it can be used for slow diffusion. You can plan like that. The change in viscosity with pressure is also a factor. It is not the temperature. Temperature is the easiest thing. Pressure, if I want to increase or decrease, either I have to take it to a higher altitude or to a lower altitude. At room temperature, pressure increase will be always a challenge. So, that is why we use temperature for an advantage and keep playing with the viscosity. The change in the viscosity with pressure is also a factor, but temperature is often dominant influence for many common fluids. For example, sometimes people also say that when you want to paint a wall which is made out of steel or any metal, so then what they say is you slightly preheat the surface so that what happens, the residual water whatever is there gets removed. Wherever there is entrapped gas which is there, that gets removed and the paint can be done very fast. So, temperature plays a very important role. Next important thing is surface tension. The surface tension is a property of a liquid interface with another liquid or gas, is surface tension. If the surface tension is very high, it is very hard for you to do a thin film with a liquid. It can be conceptualized as a force per unit length in SI units of Newton per meter, acting normal to a cut in the interface and parallel to the surface. Cut to the interface. So, this is the interface. So, this is interface, cut to the interface and parallel to the surface. Alternatively, it can be viewed as a surface energy per unit area Newton per meter. The molecule at the surface attracts each other more strongly than those deeper within the liquid, creating a tension. So, because of this tension only, the mosquito is able to glide on the water surface, or it is able to stay on a water surface. Molecules at the surface attracts each other more strongly than you go deeper. So, because of this, you have a surface tension which stays on the fluid. Right? Molecules at the surface attracts each other more strongly than those deeper within the liquid, creating this tension. If the interface is curved, the surface tension causes a pressure difference across the interface, with the pressure being higher on the concave surface. If you have a curved surface, then what is the phenomena we are seeing? If the interface is curved, the interface majority of the time is flat, When we do the wettability study, we always put a drop of water on top of a flat surface. You can also do it on an angled plate, but that's a different story. Now we are talking about a curved one. If the interface is curved, the surface tension causes a pressure difference across the interface, with the pressure being higher on the concave surface. Next is capillarity. I take a water tank filled with water, I keep a sponge on top of it. Now there is a diffusion which happens to the sponge. So the water gets absorbed into the sponge, right? I replace it with oil, nothing happens. Then I apply pressure on this sponge, then yes, oil gets seeped inside, right? So what is the next thing is capillary. And nowadays when we are trying to look at microchannels, we are trying to see, because by capillary action itself can the fluid fill up against the gravity inside a tube for any reaction or application. The capillary rise or capillarity is a phenomena in which liquid spontaneously rises. The liquid spontaneously rises or falls in a narrow space such as a thin tube or in the voids of a porous material. This is what I was talking to you about, the sponge. So when we try to keep a straw on the surface, you should realize that there will be a surface tension. So it is always better to push it little down where the surface tension are little low, then you can apply vacuum and then drag the fluid into your straw. The surface adhesion force or internal cohesion present at the interface between a liquid and a solid stretch the liquid and forms a curved surface called meniscus on the top. This is the meniscus. The surface adhesion force or internal cohesion present at the interface between the solid and the liquid. This is a solid and the liquid. Between a solid and a liquid, stretch the liquid to form a meniscus. It can either be concave or convex depending upon the liquid and the surface. So you can try to play with the surface. For example, you try to take a straw or a pipe, you internally coat it with some other fluid, allow it to dry, and then you can start playing with stretch the liquid and forms a curved surface called meniscus, can be concave or convex. Compressibility in the fluid flow. Compressibility refer to the change in the volume or density due to pressure change, which is, water, when you even apply pressure, it's going to be very, very less. Two coefficient measures compressibility at rest are the isothermal compressibility coefficient and isentropic compressibility coefficient, both having the dimensions of inverse pressure. The fluid motion, the question arises whether pressure variation significantly influences the volume change of the fluid. It is very rare that compressibility of a fluid is going to change in liquids. In gases, yes, right? There are two parameters which you have to know: isothermal compressibility coefficient and isentropic compressibility coefficient. Both are very important for a liquid. As isovolume evolution is one where fluid volume remains constant, the characteristics of an incompressible fluid comes into existence. When density changes can also occur due to temperature or composition, an isovolume evolution is equivalent to constant density evolution when the fluid is homogeneous and monophasic. The influence of the fluid compressibility on the general flow pattern is related to the Mach number. So in gases, we talk more about Mach 1, Mach 2, Mach 3. For example, the fighter planes go at Mach 1, Mach 2, Mach 3. So the influence of the fluid here in airplane and all is gas. But when we talk about fluid as a liquid, the influence of fluid compressibility on the general flow pattern is related to the Mach number. So, we call this with respect to Mach number. The flow where compressibility effect are significant are called as compressible flows. The liquid are typically treated as incompressible and the gases are highly compressible. The next one is vapor pressure and cavitation. Surface tension leads to cavitation. Vapor pressure is a pressure at which the liquid boils and is in equilibrium with the own vapor. Cavitation is the process where vapor bubbles appear in the liquid when the liquid pressure falls below the vapor pressure due to the flow phenomena. So, you have a flow which is fluid flow which is coming. There is a convergent divergent nozzle. So, it converges, then there is at the middle there is a pressure drop. Once there is a pressure drop, then cavitation is formed, bubbles are formed. Cavitation is a process where vapor bubble appears. These are vapor bubble appearing in the liquid when the liquid pressure here falls below the vapor pressure. The vapor pressure is very important, falls below the vapor pressure, then these bubbles are formed. And these bubbles, as you know, when they are formed, they have a vapor pressure, low pressure and all. But when they try to expand and burst, they create a high pressure, localized high pressure bursting will happen, like very small bombs, it will burst. And this cavitation can be used for killing germs. This cavitation can be used for removing dirt along the surface. This cavitation also can be used for mixing. So, moment there is a turbulence created, mixing can happen. So, the cavitation is a very important process. Cavitation is a process where vapor bubbles appear in the liquid itself. Here you are not blowing air. By a pressure drop, you are trying to play with the liquid. Appears in the liquid when the liquid pressure falls below the vapor pressure due to the flow phenomena. The cavitation number is a dimensionless parameter describing flow-induced boiling. This is flow-induced boiling. So, cavitation bubbles are formed, and then the bubbles get expanded, then the bubbles collapse, releasing intense energy. That is what I said, small bombs. So, it can be used for multiple applications. So, vapor pressure and cavitation is very important. Next comes the bulk modulus and its indicator role. The bulk modulus is related to resistance to compression, and you know liquid it is incompressible. So, here the basic elastic modulus definition, Young's modulus you can try to have. Young's modulus we saw in materials course, where E is nothing but stress by strain, right. Then we see here the Poisson's ratio. Poisson's ratio is you try to compress, you see what happens to it. Then you try to have a shear modulus where you try to shear on the top and there is a bottom locking shear. You can see the shear modulus can be figured out. Then the bulk modulus is you try to compress it from all sides, right. From all sides you see the bulk modulus. So, you see here you compress from top, side and the other side. So, the bulk modulus is related to resistance to compression. While not explicitly defined as bulk modulus in the text, its unit and context suggest it is a measure of fluid resistance to volume change under pressure. So, you are trying to put a fluid, compress it, like what happens to an element, fluid element, you take it deep into water. Liquids are described as a nearly incompressible, indicating a very high bulk modulus. Means that a very large pressure change can cause a very small change in the volume. So, it is given by Newton per millimeter square. So, the bulk modulus can be represented as K. Specific heat. The specific heat is defined as an energy required to raise the temperature of a unit mass of a substance by 1 degree is specific heat. I keep a container filled with crude oil. So, what is the energy required to heat and raise the temperature of the unit mass by 1 degree is specific heat. In general, the energy depends on how the process is executed. In thermodynamics, we are interested in two kinds of specific heat. One is specific heat at constant volume Cv and specific heat at constant pressure Cp. So, Cv and Cp are very important properties. The thermal conductivity of a fluid, it is very important. I apply heat in a container, and how is the heat getting distributed? This is heat. How is the heat getting distributed in the container? So, that is thermal conductivity of the fluid. So, sometimes the thermal conductivity is very high, so it can quickly conduct. Sometimes it is low, so it takes a lot of time to get heated up. So, the thermal conductivity is a fluid property that characteristics specific fluid mechanical behavior. It is a measure of the ability of the material to conduct heat. Many a times at room temperature or at 50-60 degrees, it does not even conduct heat. Maybe once it crosses 70-80 degrees, then it starts slowly conducting heat. According to Fourier's law of conduction, the vector heat transfer per unit area is proportional to the vector gradient of temperature. So, Q is represented as minus K times delta T. This K is thermal conductivity. This means that the heat flux is equal to minus K times the temperature gradient. So, I repeat, Fourier's law of conduction states that the vector heat transfer per unit area is proportional to the vector gradient of temperature. Vector heat transfer per unit area is proportional to the vector gradient of temperature. With thermal conductivity being a constant of proportionality, this means that the heat flux is equal to minus K times temperature gradient. So, if you see the effect of temperature with respect to thermal conductivity of a fluid, it can increase and then decrease. Many fluids it can increase and decrease, some fluids it can go constant. It all depends. The thermal conductivity K of a fluid varies with temperature and pressure, similar to viscosity. For a gas, thermal conductivity depends on the density, mean free path, because the temperature has to transfer. So, it depends on the mean free path, the gas constant and absolute temperature. But in fluid, it varies with temperature and pressure, similar to viscosity. The effect of temperature. The temperature generally has a significant effect on the density of the fluid. The density of the gas is inversely proportional to the temperature. This means at temperature increase, the density of the gas decreases. For example, the density of water at 1 atmosphere changes by 2.3%, while the temperature increase from 20 to 75 degrees Celsius. So, the effect of temperature generally has a significant effect on the density of the fluid. The density of the gas is inversely proportional to the temperature. The density of the gas is inversely proportional to the temperature. When the temperature increases, the density decreases. This means as the temperature increases, the density of the gas decreases. For example, the density of water at 1 atmosphere changes by around about 2.3% when the temperature increases to from 20 degrees Celsius to 75 degrees Celsius. Density of water at 1 atmospheric pressure. You can see what is the percentage increase. The temperature has a strong influence on the viscosity. As I told you, the viscosity decreases with increase in the temperature. The temperature has a strong effect on the viscosity of the liquid. Specifically, the viscosity of the liquid decreases as the temperature increases. This is why hot oil appears to flow faster than the cold oil. Cp and Cv, constant pressure and constant volume in a fluid. So, Cv can be viewed as an energy required to raise the temperature of a unit mass of substance by 1 degree as the volume is maintained constant. So, a container is filled with water. So, now you are trying to heat it. So, the volume is constant, mass is 1 kg, delta T is to increase by 1 degree Celsius. Cv can be calculated by this way. What is the heat required to increase it for a given fluid? Cp can be defined as a change in the enthalpy of a substance per unit change in the temperature at constant pressure. So, here we maintain a constant pressure. Pressure is constant, mass, temperature rise, and then you have Cp is equal to 5.9 times kilojoule kg percent. So, you should know Cp and Cv are two different terms. Cp for a given condition can be higher or it can be lower. The significance of thermal expansion. The thermal expansion can be used for raising an alarm, for ejecting or reducing the pressure, whatever it is. Thermal expansion is a very important phenomena. Thermal expansion refers to the phenomena when the volume of the substance changes with temperature, typically discussed at constant pressure. At constant pressure, the volume increases. When subjected to a temperature rise, the fluid media undergoes a volume increases. It expands. Friends, can you think of an example what you see in your day-to-day application? When you heat it, the volume expands for a liquid, and when you try to reduce the heat, it shrinks. Many of the polymer does it. Polymer, they do this phenomena. You heat it, it expands, and you cool it, it shrinks. Right? Like that, you can also think of some examples with respect to your day-to-day applications. This change can also be viewed as decrease in density. The thermal expansion is significant in fluid because it affects the density variation within the fluid. It affects the density variation. In situations involving temperature difference, thermal expansion can lead to density gradient, which undergoes the influence of gravity, create buoyancy forces. Look at it, how things are getting related. These buoyancy forces are the driving mechanism behind the natural convection when the fluid motion is caused by density variation resulting from a temperature difference. See how everything is linked. You are linking the temperature in situations involving temperature difference. The thermal expansion, you increase temperature, the thermal expansion leads to density gradient. True, right? The volume increases, which under the influence of gravity creates buoyant forces. What are buoyant forces? Which you would have studied, why does a ship float? Buoyant force. These buoyant forces are the driving force behind natural convection. Natural convection is hot on the top, cold in the bottom, there is a convection, where fluid motion is caused by density variation resulting from temperature difference. Why are ideal fluid non-viscous? Ideal fluids are considered non-viscous because their definition explicitly sets that the viscosity coefficient is 0. This aligns with Newton-Stokes scheme, which relates shear stress to the rate of strain. In an ideal fluid, this relationship implies no resistance to shear. So, that is why the ideal fluids are non-viscous. This absence of shear stress or internal friction is the defining characteristics that makes an ideal fluid non-viscous. Unlike real viscous fluids where shear stress causes continuous deformation, an ideal fluid offers no resistance to deformation because mu equal to 0, resulting in 0 shear stress, tau equal to 0. So, that is why ideal fluids are non-viscous. So, what is the difference between ideal fluid and real fluid? The viscosity makes the big difference. Viscosity in real fluid have non-zero viscosity. Mu is always greater than 0. offering resistance to flow and deformation. The ideal case, mu is equal to 0. The thermal conductivity of a real fluid has a non-zero thermal conductivity where lambda is greater than 0, allowing heat transfer by conduction can happen in real fluid. But in ideal fluid, it is a non-heat conduction, so lambda equal to 0. Irreversibility. Real fluids exhibit intrinsic irreversibility due to the viscous dissipation and heat conduction. Because of these two, there is irreversibility in the real fluid, but in ideal fluid develops no intrinsic irreversible during discontinuity free motion. So, this makes the difference between ideal versus real fluid. The real fluid adhere to solid surface. The non-slip condition where both normal and tangential velocities are 0 relative to the surface at the boundary condition. Ideal fluid are assumed to slip along the solid surface. So, this is ideal fluid, this is real fluid. Where real fluid, friction is not 0, so you will always have this distribution. Friction is not equal to 0, real flow mu is not equal to 0, energy loss is not equal to 0. But here everything is equal to 0. The Reynolds number, ideal fluid motion corresponds to an infinite Reynolds number. We saw what is Reynolds number in the last class. There is Reynolds number will try to tell us lamellar flow and turbulent flow. Right? So, it is infinite for an ideal fluid, whereas for a real fluid it will have a finite Reynolds number. The assumptions, what we do is assuming the fluid is ideal significantly implies analysis by setting mu equal to 0, lambda equal to 0. It eliminates terms related to viscous stress and heat conduction from the governing equation of motion. For an ideal incompressible fluid, the energy equation becomes trivial when temperature remains constant along the particle path if infinitesimally homogeneous. So, in order to generalize or simplify the governing equation, we always try to take the fluid as ideal fluid, where we try to remove viscosity, we try to remove thermal conductivity. Simplify boundary condition with no slip condition, which is often mathematically complex, is replaced by a simpler condition that normal velocity at the solid surface is 0, allowing slip in the tangential direction only. So, these two are the assumptions we make such that the problem can be solved. So, the governing equation mu equal to 0, lambda equal to 0, where the governing equation mu equal to 0 and lambda equal to 0, and the no slip boundary condition will get activated, where we only allow to see the tangential direction forces, velocities. The viscosity change of gas. For gas, the viscosity also varies strongly with respect to temperature. However, unlike liquid, the viscosity of the gases increase with temperature. Kinetic theory suggests that the transport coefficient, including viscosity, tend to increase with temperature rise for a gas. The influence of surface tension versus temperature. The coefficient of surface tension gamma of a liquid decreases with the increase in the temperature. The surface tension is 0 at a critical point. You can also bring the surface tension 0. What is surface tension 0? The attraction between the molecules on the surface is 0. For common interface like water, air or mercury, air, measured surface tension values are provided at a standard temperature of 20 degrees Celsius, indicating its dependency on temperature. So, it plays a very important role in density, viscosity, and it also plays an important role in surface tension. So, the effect of vapor pressure. The vapor pressure is a pressure at which the liquid boils and is in equilibrium with its own vapor. As the temperature increases, vapor pressure of the liquid also increases. When the liquid pressure falls below the vapor pressure, the vapor bubbles appear and form cavitation. If you go back to the triple point what we studied, all these things you can understand. Water at normal atmospheric pressure will boil at 100 degrees Celsius because its vapor pressure rises to atmospheric pressure at the temperature. Then the last part is impact of thermal expansion is important in engineering systems, particularly in the situation where there are buoyancy forces involved. The density variation causes thermal expansion under the influence of gravity, creating boiling force. These buoyancy forces can drive fluid motion known as natural convection. Friends, to recap what we saw in this lecture, we saw what is density and its use. Then we saw specific weight, specific gravity, viscosity. We saw in viscosity different types, static and dynamic viscosity, dynamic viscosity and kinematic viscosity. Then what we saw was the no slip condition, then surface tension, capillary action, compressibility, vapor pressure and cavitation pressure and cavitation. Then we saw the importance of specific heat, thermal conductivity, then significance of thermal expansion of fluids, then what is an ideal fluid, what is the difference between real and ideal fluid. At last, with majority of the properties what we discussed, we saw the effect of temperature. So friends, we have used all these reference material to prepare the slides. Thank you very much.